Okay. The other name, okay guys, the other name for extreme value theorem is the max-min existence theorem. And do you remember what this theorem was about? There's two major theorems. This is one of them. But what does the theorem tell us? No? You're giving me conditions. What does the theorem guarantee us? The function will have both a maximum and minimum value. First, it helps to know what the theorem's about. That's what the theorem's about. Okay? Now, what are the conditions to have both a maximum and minimum? What's it?
The between the endpoints, the function.
Okay, so this is a guarantee. That's how you spell guarantee. Both max and min. Okay, shh, you guys. We need to review this because we've forgotten it. Okay, so I guarantee that the function has both a maximum and minimum value. That's what we're doing. We're reviewing all of 4.1 through 4.3. And what has to be the conditions? The function has to be continuous on a closed interval. Then we guarantee it. Okay, there it is. A function will have both a maximum and minimum value if the function is continuous on a closed interval. The highlighting pieces are the ones you really need. Now, where do they occur? At the critical points.
What are critical points?
Yeah, what are critical points? Is that next on our list? Where are the critical points? Endpoints where the derivative is 0 or where the derivative is undefined. So there it is. How do you find them? You find the maximum or minimum value of a function. You find your critical point, 0, undefined, and evaluate each of the critical points, and don't forget the endpoints, in the function. What did I have in the function? In f of x. Pardon? F prime is 0. Those are the critical points and the endpoints. So there they are. It's a multi-step process, but if you think about it, it's not that bad. I know I have a closed interval. I know I have a continuous function. I know that I'm going to have a maximum or minimum somewhere. There's my max, there's my min. Could be at the endpoints. Here, in this case, if it was down here, that'd be that's continuous. What's wrong with this? It's not differentiable. Okay? So it's a guarantee, and I'll look at the endpoints, because it could occur at an endpoint. Can I move that? No, I can't. I've changed it, problem, so let's put the minimum where it belongs. So in which case the minimum's at an endpoint. Here the minimum or the maximum is where the derivative is 0. Here's another candidate, just like in the Republican caucus in Iowa. There are lots of candidates. Not everybody's going to win. That's right. So do you understand? Do you understand what I mean by candidates? They are the potential places you will find a max or min. So you will.
What are the words for the actual max and min and then the
Maximum value of the function. Yeah, we'll get there. We'll get there. Okay. Any problems? Hey guys? Is that okay? So all you have to do is take all your candidates and substitute them into the function and see which is the biggest, which is the smallest. You're going to get both. So in the Republican caucus, there will be a clear winner maybe and a clear loser. you're going to have both a max and min. But not every candidate will be the winner. Could there be ties? Yeah, there could be ties. Could be. So which case? Which candidate would get the maximum, and then what would the maximum value be of those votes? Okay, next part. What are extreme values? Max and min. Of the function, not where, but the values of the function. I know I fall into that trap too. I want to say where it is, but that's not what it is. Make sure you read the question. Okay? When asked for a maximum and minimum value of a function, it is implied you are looking for the biggest ones, the global or absolute values. Local max and min can never occur at endpoints. That is not a true statement. I want to be clear that they can occur at endpoints. For our course, we're going to say they can't. Just keep things simpler. If you take an advanced calculus class in college, you'll find out that they can occur at endpoints. But for what we're looking for in terms of this exam, you're not going to be looking for local ones at endpoints. Local ones are going to be in the interior. So you're looking where the derivative is 0 or undefined for what our purposes are. But I don't want to tell you something that's not true. So this is not true. Nope. Oops. No, I had to check with college professors because it was different in different books. This book, this says local max can occur at endpoints. They can't. This textbook is right. It says no. Oops. And never is incorrect. Whereas my BC Calc book says they can never occur at the endpoints. And he's a college professor. So, but I did check with my group, and yes, they can. But for our class, not going to happen. Okay, are we ready to go on? That's the max-min existence theorem. That's 4.1. It's a big theorem.
We got that one.
Okay. Now, I should have said this a little bit better. Now, after I've done a number of these problems, I noticed something. And so I'm sharing with you what I noticed. If a function is continuous, hey guys, function's continuous, the derivative is 0 at a point, it could be everywhere too, but we'll just say at a point, then what must be true about the function? Not necessarily. Just because the derivative is 0, remember that's a candidate. They're not necessarily winners. But the function's going to be smooth. There'll be no corners. No abrupt changes. If the derivative is 0, then the function is changing smoothly. Okay? That's what I wanted to get out of that. Once we get that idea, we can do the next one. Function must be smooth. It might be a max or min, or it could just be a location where the tangent line is horizontal. So I can give you a picture here like this. So the slope is 0 here, but it's neither a max nor min. Remember, when the slope is 0, it's just a candidate. Here, m is equal to 0, right? If I know that the derivative is 0, I just know the function is going to behave nicely. It's going to be smooth. No sharp corners. No vertical asymptotes. So then I don't have to worry. If I know that my derivative does this, it's positive, 0, negative, and we'll review this, but remember the function is going to be what? If f prime is positive. Increasing and then decreasing. I know the concavity without doing a second derivative test. So it's kind of nice to know that. Okay, Grant. Right, we'll get to that. We'll get to that test in a second. What if the function's continuous and the derivative is undefined? It's not going to be smooth. Could be vertical. So I could have this one. That's a vertical tangent right here. I could have that, or I could have this. true about the derivative at this point? Is there cusp there? It's undefined. So this slope here on the left side is positive. On the right side, it's negative. So the first derivative line might look like this. It's positive, negative, it's undefined. So then I know I'm going to have a what? A sharp corner. So I know a lot by just looking at the first derivative. Pardon? If this changes from positive to negative, it's undefined, I have to have a sharp corner. If it's continuous, if the function's not continuous, that changes everything. All bets are off. Here, what's true about the slope here? Positive, and it's positive, so my first derivative would be going positive, positive, undefined. That is not a sharp corner. It's a vertical tangent. An example of this would be y equals the cube root of x. At 0, I have a vertical tangent. I'll let you investigate. At 0, the function's fine. At 0, the derivative is undefined. And we can do some problems. We'll do problems. But I'm just saying the first derivative tells you a lot. If it goes through 0, it's going to be nicely behaved. If it's undefined and it's continuous, then I'm either going to have a vertical tangent or a sharp corner. The sign has to change to get a sharp corner. What if the function's not continuous?
Then we can't do it.
No, if the function's not. What if we don't know if the function's continuous or not? And the derivative is undefined. What's the other possibility? We don't know if the function's continuous. What does that tell you? Right? It's not differentiable there. What has to be true for a function to be differentiable? It has to be continuous. So if I don't know if the function is continuous and the derivative is undefined, couldn't we have what? A hole. Yeah. A discontinuity. They're usually going to tell you if it's continuous. If they don't tell you, then you're going to have to check your domain and make sure you don't have a hole there or a vertical asymptote. For instance, y equals 1 over x. What if y is equal to 1 over x? Do you remember the derivative of that function? Let's just do it. Remember your power rule? We haven't forgotten everything, have we? It's negative 1, x to the negative 2. And some people said, correctly, negative 1 over x squared. Well, what happens at x equals 0? The derivative is undefined. What does this graph look like? There's some basic graphs you have to know. This is one of them. The function doesn't even exist at 0. So the derivative had better be undefined, right? Doesn't even make sense. So that's the problem. You could have a discontinuity. So if I don't know if the function is continuous or not, I have 3 things that could happen. I really don't know until I investigate further. But I kind of like the fact that if the derivative is 0, it's always going to be smooth. That's just kind of nice to know. So if you're in a time crunch and you want to worry about concavity, let's say it's multiple choice because you don't have to justify things. You can just say, oh, it's 0. When positive, 0, negative, so I'm fine. I know concavity. Reverse of the second derivative test. Okay, so these are just some thinking questions here. You may have to go back and think about it some more. Okay, there's another big theorem. We're now on page 3. And the titles of these sections are off the old book, so you can ignore that. But I think this was section 2, the mean value theorem. Remember the mean value theorem. What are you saying? Ryan? Somewhat close. That's the intermediate value. But, hey, very good. If we have a curve here, and we draw the secant line, now if you think about it, if I take a tangent line here, which isn't a very good line, but I'm going to drag it. Now notice it's negative here, right? And when I put it over here, and let's see, I need to rotate. And I put it over here, what's true about the slope there? It's positive, so it does use the intermediate value theorem. It's got to pick up every value between that negative slope and the positive slope. In particular, guess what? Oopsie. It's got to be equal to the slope of the secant line somewhere. But you got to get your continuity here. Before you can do this, you have to check to see if it applies. And I believe last year the mean value theorem did not apply. And they actually asked that question. And our students did well. If I have a continuous function, Grant, in the closed interval, are you going to come up and do this? Okay, then you better pay attention, right? And it's differentiable inside. I don't care about the endpoints there. Then there's at least one point in which, what? The slope of the secant line. And that's what we have symbolically. So that the slope of the secant, well, I've got it backwards. The tangent line equals the slope of the secant line. Remember that now? Hoping this comes back. It's just saying that if you draw this, I need to prove the fundamental theorem of calculus, and it will be on the exam. Other than that, do I use it very often? No. The slope of this line through here, there's got to be a tangent line where the tangent line's parallel to that. Or, in other words, okay, you guys? What's f prime of c? It's an instantaneous, too long a word for me, rate of change. Okay, that's your speed at your speedometer at an instant. Does anybody remember what this is called when I find the slope of the secant line? Average is equal to the average rate of change. So you can remember it either way, but I might need this. In fact, I can think of a multiple choice question which forces this issue. You need to know it this way. I should bring that in because we've had that question before. Okay? That's the mean value theorem. My diagram, should I redraw my diagram? My diagram's up there. Is that okay or not? I didn't have anything labeled like, you know, here's A, here's my C value, here's B. It's just not, I didn't give myself enough space. Okay, that was 4.2, first part of 4.2. The second part is this strictly monotonic. I don't care if you know the word, but if you want to say a function's strictly monotonic, then you're saying that the function's always increasing or always decreasing. So it might look like this, or it might look like this. How about the sine function? No. This is a yes. The thing about, if you have a function that's always increasing or always decreasing, then you have a one-to-one function. You can always find the inverse. They're not going to use the word on the exam, I don't believe. So you don't have to worry about it. So it's de-emphasized. Okay, ready to turn the page? Oh. In our old book, they call it the monotonicity theorem. But in our book, we just know something about this. If what? If f prime is positive, then what's true? If my slope, my tangent line is positive, the function is f increases. Okay? What if f prime is negative? Yeah. But if you just draw the pictures, you'll see that. Here's an increasing function. Slope's positive. I don't memorize this stuff. Okay? This is what they're looking for if they'll say, find the intervals where the function is increasing or decreasing and justify your answer. I justify my answer first. I say, oh, the first derivative, I'm going to look where the first derivative's positive. Then I can look at my picture and say, oh, okay, it's here. might be positive at a single point, but usually it's an interval. It might not be positive at all. Is that okay? Adam? Mean value there. What about concavity? What do you know about concavity? Here's concave up, like a cup. What's true about the second derivative? Look at that. You're concave up. You are happy. You're positive, right? What if you're concave down, like a frown? That's right. That's what they call the concavity theorem. I'll post all this, by the way. Inflection points is on the sheet twice, sorry. Okay? That makes sense? Now, inflection points occur when the concavity changes. But that's not how you prove you have an inflection point. So there's an inflection point. Okay, guys? Inflection point. How do you know that we have an inflection point? In this, I don't even care. It's just change the sign. You're right. Oh, look at that. Oh. Did I miss something in the last class? I might have. Oh, I did. Yeah. Okay, guys. Okay, guys. Inflection points are points where the concavity changes. You must show the second derivative changes sign. Candidates are where f double prime is 0 or undefined, but they're only candidates. No guarantees. Example of that is y equals x to the fourth, because I know that that's always concave up. F double prime at 0 is 0, but it doesn't work, because what has to happen to the second derivative? It has to change sign. It doesn't. Okay, I forgot this note. Set the second derivative equal to 0 or undefined. Okay, guys, what do you mean by differentiable? A lot of you asked this question. Okay, girls, what's it mean by differentiable? Okay, what has to happen first? It has to be continuous. The derivative exists at all points, and the function must be continuous. So that's huge when they give that to you on the exam. If they say the function is differentiable, that means you can find the derivative. You're not going to have a sharp corner, vertical tangent, and you're going to have a continuous function. Okay, you should be writing this down. Are we ready? The derivative, when you say it's differentiable, the derivative exists. And for a derivative to exist, the function must be continuous. Okay. Now, local mins occur when here's C, here's f of C, and in the neighborhood near C, f of C is bigger than all the other candidates. It's a bigger value. More volts. What if you're talking about a minimum? What's true about your f of C here? It's smaller than all the other elements in the neighborhood. Okay, Grant, do you remember the first derivative test? Well, look at the picture here. What's true about the slope? I have a maximum here, right? Slope is positive, and then it's 0, and then it's your first derivative test. If f prime, now the picture is not sufficient, but if it goes from positive to negative, I don't even care if it's 0 or undefined there. This is a max because f prime, let me do that. F prime changes from positive to negative. That's the first derivative test. What about a minimum? Oh. So here's f prime. This sign graph is helpful. I want to see it myself, but they will not give you any points. Then my functions decrease and increase. And remember, if it goes through 0, it's very smooth. So f prime goes from negative to positive. We have a minimum. Yes, you get your points for writing that. And if you just give them the sign chart, you get nothing. Well, I thought it wouldn't make any difference, but I found out it did. A lot of people could do the sign chart, but couldn't verbalize it this way, which surprised me. So you have to communicate to the reader that you know what you're talking about. The sign chart just means you filled out signs. It doesn't mean you know what happened. Because I know the function's decreasing and increasing. You could say functions decreasing and increasing. Okay? So that's what we have here. F of x has a maximum when f prime of x changes from positive to negative. And you can do it with symbols like I did right in here. Grant, let's see how many times I say your name. Okay. Second derivative test. Do you know that one? They can force the issue. We're going to do a problem today that does use the second derivative test. Do you remember what the second derivative test is? Well, here's my function, f of x. And this clearly is a minimum, right? At this value, at c, right? What's true about the second derivative at c? This is concave up. That's right. And if we have this one, which is clearly a maximum at c, what's true about f prime of c is what? Negative, because you're concave down. It's counterintuitive to me. I want to mix them up, but I don't. Sometimes I'd probably do. So that's the second derivative test. First, you have to find the c value, and you have to use the first derivative. So you have to use f prime is equal to 0 or undefined to find c. And then you evaluate f double prime of c. And if it's positive, that means my function's concave up at that point. If it's negative, it means it's concave down at that point. And then I just draw the picture. Oh, it's a max or it's a min. And they can force that. They will force it. You will see one question on the exam that will ask that question. They'll force you to do that. Inflection points we already did. So we don't have to do that again. So what we did in the other class, and I think it was good to do that, is we did problems. We did a couple problems out of the book. We did 38. I just want to do one. Out of 4-3. Now your homework is going to be to finish 4-3 or to do 4-3 if you haven't done it. Tomorrow we're going on to max mins. If you've done it, you may need to review it. And on this handout I'm giving you, we're only going to do 1 and 4 tonight. That's it. Whoops. I probably want to punch these, but. And we did this problem, we did 38 out of the book. So let's do 38. I don't know if it's a homework problem or not. Because some of you, I don't think you know. much about the second derivative test. Okay, you guys. Now, you guys, shh, listen. It says on 38, use the second derivative test to find the local extreme values of the function. They don't want where it occurs, although I got to find out where it occurs before I can find out what the value is. Oh, did I miss you guys? I'm sorry. That's because I was going to be clever this time and I wasn't. So we're going to first do 38, and then we can look at the very first problem on here. Let's see where we get. Now, these are AP questions. Stole it. Okay. So, you know what makes this hard? Now, when I did my solutions, you guys, sometimes, if it said just do a, show if it's max and min, I would do both tests as long as the second derivative was manageable. Sometimes the second derivative is not nice. This one's not terribly bad, but it's not exactly easy. This is the second derivative.
This is e to the x, e to the negative.
Negative x. Right. There. Okay, ready? Do you remember how to find the first derivative? Product rule? So it's x times the derivative of e to the minus x. It's e to the minus x times the derivative of the inside function, which is negative 1. You're correct, Grant. Remember the chain rule? It's the derivative of e to the minus x, which is the same function back again, times the derivative of the inside function. Okay, that's the first part. Plus, then you leave e to the minus x alone, and you take the derivative of x. Remember the product rule. Put a dot there if you need to. And that's 1. Is that okay, Adam? So I want to simplify that. So what I'm going to do is factor out e to the minus x. So you should be ahead of me. And I'm left with what? I took this one out, so what am I left with?
Negative x plus.
Negative x plus 1. Now, I'm looking for the c values. No matter what I do, I still have to find where the derivative is 0 or undefined. It makes no difference. So, is this derivative ever undefined?
No.
There are some basic functions you need to know. You need to know what e to the x looks like and e to the minus x. E to the minus x looks like this. You're right. It's never negative, never 0 even. Okay, so the only place I have to look at for this being 0 is when minus x plus 1 is 0. Now, just use your head. What's x equal to? X equals 1. Now, we could do a first derivative test, but it specifically said do a second derivative test. So do you want to take the derivative of this form or the original form, which is right up here? It makes no difference. I think the second one's a little easier. This is 0. Correct. So that's our critical point. And I need the second derivative to tell me if it's concave up or concave down at that point. So let's find the second derivative. Let's use this form. It doesn't matter, because all I have to do is take the derivative and substitute in 1. I don't have to simplify it. So I want to, but... So it's e to the minus x times the derivative of minus x plus 1. Negative 1. Plus, and a minus x plus 1 times the derivative of e to the minus x, which is minus x times negative 1. And let's just put in the 1. That's all I care about. I don't have to simplify that. So let's keep it simple, right? So I want f double prime of 1. So it's e to the negative 1 times negative 1, whatever that is. And what happens to this? It's 0. So 0 times any number is 0. I'd like to simplify this just so I can see what's happening. It's a negative 1, and e to the negative 1 is 1 over e. So is that positive or negative? What is e? 2 point. It's just a number between 2 and 3. It's about 2.7. It's just a number. Okay, this is clearly less than 0. The second derivative is negative, so that means my function is concave down. Therefore, this is it's a negative number. 2.7 is positive. Remember, e to the negative 1 is just a reciprocal. And you know what they're going to do on the exam? They're going to give you lots of e to the x's and ln's. Okay, so this is at x equals 1. This is f. That's going to be f. So what's true? Is that a max or min? The maximum. Because f double prime is positive. Now, I almost forgot to answer the question. They didn't ask where. They asked what's the value. So what do you have to do with 1? Yep, put it back in here. So f of 1 ends up being 1 times e to the negative 1. I leave it, but it's 1 over e. So it's about 1/3. Kind of interesting. Not too bad. But the minute you get something where you have the quotient rule to do the second derivative, it gets really ugly. So I'd like to not have to do that. But they can force a second derivative test. Okay? That's what the homework looks like. Especially do the ones with the pictures, because there are some pictures. And on this little handout, we're only going to do 1 first problem and 4. 4 has the pictures. Okay? It's all pictures. It's the only thing you can't do, well, some of you may be clever enough to figure out how to do 4D. We really haven't covered it. So you're going to do 1, it's A through C. You don't know how to do D. And 4, A through C. But you could figure out D. If you're clever. You do have to use the max min existence theorem on 4D, by the way. But you don't know how to integrate. So that's why it's hard. Should we do the first problem together? Now, this is a graphing calculator problem. I'm sorry it doesn't say it, but it is. And this is going to review some old material. And we have a final exam coming up. Now, those are dummy variables. I don't care if it's t or x. The thing is it says the particle moves along the y-axis for t greater than or equal to 0. So it's moving up and down on the y-axis. Not really that important. Okay, find the acceleration of the particle at t equals 2. Now, at time t equals 0, the particle's at negative y equals negative 1. Don't worry about that. That's for part D. Don't need it for any of the parts we're going to do right now. And if you can get A through C on these problems, you're looking at a 4 or 5. If you can consistently do most of the problem and not get to the last one, it's okay. Okay, so first off, what mode should we be in on our graphing calculator? Radian. Now, I don't know how this problem was graded, but lately, sometimes you get points for the intent, your intent. So it asks for the acceleration. How do you find the acceleration? The derivative of the velocity. Now, if you write that and you're in degree mode, you're going to get the wrong answer. But it could be you might get something for saying that the acceleration is the derivative of the velocity. It's definitely worth a chance. So if you get the wrong answer, I know you get nothing. But if you at least write this, maybe it's a 2-point question. It's just the way they're working it these days. They want to know if you understand what you're supposed to do. And I want the acceleration when t is equal to 2. So how are we going to do this? We're not going to do it by hand. This is a graphing calculator problem. Do you remember what we used? What was it called? And derive. And I'm going to put this into y1. I'm going to use x's because they're dummy variables anyway. Otherwise, I have to put in t's and I have to use the alpha key, and that's too much work. So we'll do y1, comma x, comma 2. If you have the old-fashioned one. Otherwise, it's going to look like what I have right here. Anybody at the calculator out? One person does. Let's see what we get here. Make sure you're in radian mode. I have an answer for them from last class. I need the answer because I can't do part B without it. Negative 0.13. I need at least 3 places. 2, 9. Okay. I write them all because even if all of these are wrong after the first 3, we don't look at it. So if your first 3 digits are correct and everything else is wrong after that, it doesn't matter. You still get your point. So I would write them all. That'd be safe. Then I don't have to worry about it. It just kills us when you give us negative 0.13 and we have to take the point away. We do not like that. So always 3 places, minimum. You can truncate it or round. Either way, they're both correct. Yeah. Okay. B is the speed of the particle increasing or decreasing at t equals 2? So what does that mean? If the speed's increasing, what's the particle doing? Speeding up or slowing down? Do you remember how to do that? How do you know if the particle's speeding up or slowing down? Uh-uh. You have to give a calculus answer. Do you remember that if A and B are the same sign, it's speeding up? And if they are different signs, it's slowing down. I know it seems crazy, but if the acceleration and velocity are both negative, think of my pen falling. If you jumped out of a tall story building, you are not slowing down, are you? Acceleration's negative, velocity's negative, you are speeding up. So if you keep, remind yourself of that. Or if you jump out of a plane, you're going to speed up, right? So the acceleration's negative. What's the velocity? Can we find v of 2? Now, how do you do it on your calculator? Those of you who have your calculators out, you have this in y1. On your home screen, just type in y1 with parentheses, function notation, 2. Somebody want to tell me what that number is? 3 places. 0.43 what? 6. They're both negative, so what's this doing? It's speeding up. We don't say accelerating. It's not the question. It's speeding up. That's better. Yeah. That wasn't too bad. Now, it says for C, find the time t greater than or equal to 0. It's not a closed interval, unfortunately, at which the particle reaches its highest point. How are you going to find the highest point? Well, you have a velocity here. Highest point is when the velocity is. I throw a pen up in the air, it's going to stop. Velocity is 0. It's got what? But that's not enough. Velocity is 0. I mean, I could be going left and then stop and keep going left. I have to change direction. So what has to do about the signs? Right. S prime, which is V, has to change signs. And they're not going to trick you. If it says highest point, it's the highest point. So you can think about it. It's a maximum, then I need to know that V does what? It goes from positive to negative, and it's going to go through 0, but where? So that's what they ask. When is this happening, right? Okay, so all I have to do is what? And this is a graphing calculator problem. Set my velocity equal to 0. We could do it algebraically, but we don't have to. So I'm not going to. Whatever works the best for you. So V is V of t equals 1 minus inverse tangent. Don't forget the inverse part of it. So 0 equals this. It's a graphing calculator. There is another option. If you don't want to graph it, there is a solve command on your calculator that will do it as well. You don't have to have a CAS. I can show it to you. Right now? It's kind of cool. And I guess we'll do our quizzes tomorrow. It doesn't take long to teach optimization. It just takes long to do it. And I'll try to see if I can reduce that assignment so it's more reasonable. They're nice problems. I know you won't think they're nice, but they are nice problems. Now I'm going to put this in Y1. You're using solver, but there's also a solve, which I like better. What happened to my calculator? Did they change me? Oh, there it comes. It's having its issues. I mean, it's really easy on the cats. It's on the 83s as well. I think they did something to the... I know they did. Okay, I'm going to clear this out. Okay, in Y1, I'm going to put in 1 minus inverse tangent. Don't forget to do that. Is e to the minus t? Minus x. Oh, is it just x? Oh, yeah, sorry. Okay. Whoops. Okay, so I'm going to quit. Now, there's a solver command, but I don't like that one. I like to go through the catalog. Where's catalog? It's hard for me to see that. Where, do you see catalog? Above 0? Okay, there's second catalog. If you don't know about this, you should. Grant, would you have a seat, please? And it's already in alpha mode, so all I have to do is type in S, if I can find it. Must be there. Okay, and unfortunately that's it. That's as far as you get. They won't let you type in solve to find it. You can't type it in like you can on a Inspire. So it's kind of painful to get to, especially when they have all this stuff. Every function that's on this calculator is in that catalog. There it is. Unfortunately, solve is not in a drop-down menu. I don't know why. See if I can remember. I want Y1. Yeah. The solver works too, but it's more confusing. That's what I typed a 5 by accident. Don't worry about it. By accident for X. I think that's all I need. It's been a while since I've done this now. No, I probably have to give it. Where's my calculator? There it is. I gotta figure it out. Oh, what happened to the X's here? Weird. Okay, it's time to go. I just have to remember how to do it.